Here we have a problem that incorporates both Hardy-Weinberg equilibrium along with completing a chi-square analysis. In this experiment, we can see that we have scientists that have collected data on 100 lizards, and they've given us the number that they've observed for each of these three phenotypes of the 100 lizards in this population. And so what you need to do now is, thinking back to your chi-square formula, right? We need both our observed numbers and our expected numbers. So the observed numbers are already given to us here. So we need to solve the expected number. And the way that you solve for the expected number is by using our Hardy-Weinberg equilibrium equations to calculate what you would predict the phenotypic or the genotypic frequencies would be in this population if it were in Hardy-Weinberg equilibrium. So once we get our expected values, we can then compare them with the observed values and complete a chi-square analysis. So the first thing we need to do here is solve for our P and our Q values using the Hardy-Weinberg equilibrium equation. Now, what do those variables mean? So if you remember that P, that's going to be equal to your frequency of your dominant allele. Q will be your frequency of your recessive allele. Once you solve for P and Q, you can then solve for P squared, right, which is your homozygous dominant, the frequency, right, of your homozygous dominant. 2PQ is your frequency of your heterozygous, and Q squared is your frequency of homozygous recessive. Now, what we can do with this data table on the left here is go ahead and extend it a little bit. So if I were to extend it, right, just go ahead and make an extra addition here. We can make this last part here our number expected, right? And we're going to be filling in those numbers there. So the numbers that we would expect there, right, for our homozygous dominant genotype would be our P squared value. So here I'll go ahead and write P squared. And that's a frequency, right? So we need to multiply that by the number of individuals in this population. And if you see, the number of individuals in this population is 100. So what I can then do is do P squared times 100, and that would give me my number of expected for the red phenotype. For my purple, that's my heterozygous, so it would be 2PQ times 100. And then for my homorecessive, it would be Q squared times 100. And so this would now give us our three numbers of what we would expect of each of these three phenotypes in a population of 100 lizards if they were in Hardy-Weinberg equilibrium. You can then compare what you observed and what you expect and solve a chi-square analysis. All right, now how do we go about solving for our P and for our Q values? So in this next step, we now need to use our first equation, our P plus Q equals 1. And we can use that equation because, remember, P is equal to the frequency of your dominant allele. And if we look here, for our homozygous dominant, we have 75 individuals, right? And if we have 75 individuals, well, each individual carries 2 alleles of the big A. And so what we're trying to do here is count the number of big A's, the dominant alleles, in this whole pool of alleles. Now, what is our total number of alleles going to be? Well, we have, right, so our number of alleles is going to be equal to 2 times the number of individuals. And we have 100 individuals, right? So this would be equal to 2 times 100 individuals. So we have a total of 200 alleles to work with. Now we need to solve for the frequencies of each of these alleles. So how do we solve for that? For our big A allele, right? So for the frequency of our big A, that's going to be equal to, so we have 75 that are homozygous dominant, and since they each carry 2 copies of the allele, we'll do 75 times 2. Then we need to add for the purple allele. Notice that the purple genotype has 1 dominant allele, so that means they are going to have 15 of those. So we go ahead and add 15 to this. This gives us a total of 165 dominant alleles. Now for our frequency of our recessive alleles, we do the same thing, but this time we're going to use our blue, right, our homozygous recessive. And notice that we have 10 individuals, and they each carry 2 recessive alleles. And for our hetero, we've got that lowercase allele there, so we have to add 15 here as well. This gives us a total of 35 alleles. Now, these are the numbers of alleles, but we need to find their frequencies. And so we already solved for the total alleles here, where we have 200 alleles. So we need to divide these by 200, and that will now give us our frequencies. Okay, so now these frequency values have essentially given us our p-value, right? So here in the front, I'll go ahead and write p is equal to, and the bottom one has given us our q values. And again, we can double check our work because 0.825 plus 0.175 is equal to 1, right? So p plus q is equal to 1, so that all makes sense. Once we've solved for our p and our q values, we can now use our second equation of the Hardy-Weinberg equilibrium to solve for our p squareds, 2pq's, and q squared. Each of those numbers can then be plugged into here and multiplied by 100 to get our number of expected for each of the 3 phenotypes. So let's go ahead and work through that. So for our p squared value, okay, so down here, p squared, that's going to be equal to 0.825. We square that, which is equal to 0.68. Great. Our 2pq is going to be 2 times 0.825 times 0.175, and that is equal to 0.29. And our q squared is equal to 0.175 squared, which is equal to 0.03. Now remember, these are each frequencies again. And so we need to change these 3 numbers into from a frequency into a number. And so if 68% are of our p squared, right, are homodominant, well, out of how many individuals do we have? Well, remember in the beginning, we're working with 100 lizards here. So we need to multiply this by 100. That gives us 68 individuals. This times 100 gives us 29 individuals. This times 100 gives us 3 individuals. Now these 3 numbers are what we can now plug into this last column. So if I go ahead and erase what I've written in those columns for now, we can go ahead and replace them with the new numbers that we have generated. Okay, so for our red homodominant, we have 68 individuals. For our heterozygous, we have 29, and homorecessive, we have 3. Now we've reached the point where we have both an observed number and an expected number. This lets us now solve for our chi-square value using the chi-square equation. So let's walk through that last part now. So for the chi-square, we have our observed minus our expected. And so if we go ahead and solve for our chi-squared, so our first observed number is 75 for homozygous dominant, and we subtract by our expected, which is 68, divided by, or we have to square that, and then we divide it by our expected value, which is 68. We go ahead and add this to for our heterozygous, right? So 15 minus 29 squared divided by 29 plus 10 minus 3 squared divided by 3. If you go ahead and plug these numbers into your calculator, you would now get a chi-square value of approximately 23.8, give or take, depending on how many decimal places you used in the previous calculations. But regardless of that, you'll notice that this value is quite close to our final answer here, D, right? So our answer for this question will be D, 23.1, for the closest chi-square value. Now, one thing to note when solving these types of problems, some of these questions, instead of asking you to solve for chi-square, they might ask you to find the appropriate critical value or to do the full analysis using the degrees of freedom. So one part where a lot of students get mixed up is figuring out how many degrees of freedom you should use when solving these types of problems. Now, what you would expect is looking at the data, you see that there are 3 different categories, red, purple, and blue. So to find your degrees of freedom, a lot of students will do 3 degrees of freedom minus 1. So this gives you a total of 2 degrees of freedom. But in fact, that isn't correct. And the reason for that is because when we're doing Hardy-Weinberg equilibrium based chi-squares, if you know what the big A allele frequency is, or if you know what the little a allele frequency is, right, knowing one of these alleles can give you the other allele frequencies because of our P plus Q equals 1 equation. And what that means is, since you know the other by just knowing one of them, in fact, you only have 2 categories here. So when you're calculating for your degrees of freedom, this would actually be 2 minus 1. And so you, in fact, only have 1 degree of freedom. So what this means is, since you only have 1 degree of freedom, you're actually going to be using the 3.84 value here, right, most of the time. Right? Most of these problems are assuming you have a 0.05 p-value, and since you only have 1 degree of freedom, the 3.84 would be the value that you use instead of the 5.99. So don't get tricked by that. Hope this helps.